Who designed that?
Cisco. But they came up with routers, so it was great. So, put my memory over here. So I initialize file select register 0 to be 80 hex. And now I move a 10 into W and I say my push W reg. So what does my push W reg translate to in assembly language? Remember, my push is a macro I've defined.
Is that a pre-inc 0?
Yeah, so this will translate to move FF. And then arg, whatever I put in my arg, which in this case was W reg, comma, pre-inc 0. So each of these my pushes is basically this instruction.
I have a question.
Okay.
Well, I understand because like if you use move FF, it probably gives you more versatility, but couldn't you just use move F since you're just doing it from the working reg?
I could, but if I wanted to say something like my push adcon 0.
Yeah, that's not saying it gives you
Right.
more versatility.
Yeah,
than
yeah.
Okay.
So this is what my memory looks like. We don't know what's in here right now. This is what the file select register is equal to. What happens when I execute this instruction? So I'll write down W reg 2.
Want to put 10 into 80 and then increment it to the next one?
Does that sound good? You're close.
Would it go to address 10 and increment address 10?
It's going to move W reg, which contains a 10, somewhere into memory. It's going to move it into the location pointed to by FSR 0. But because I said pre-inc, it's going to increment FSR first. So what this instruction is going to do, it's going to see the pre-inc, it's going to change FSR to 81. And then it's going to take WREG, which is 10, and it's going to store it at location 81. So this will be number 10. These are decimal. So it'll store a 10 in location 81. Then I put a 20 into WREG, and I do the same instruction again. So it will do the pre-inc, so it will say increment this from 81 to 82, and now store W at location 82. That's where it'll put my W. Yeah?
Is there any benefits you gain from doing it pre instead of post?
Yes, I'll see that in a second.
Yeah.
It's a goofy benefit. Okay, and then the third round, I set this to 30. I move that into a pre-inc 0, which says increment this to 83. Put W into location 83. There's my 30. Okay, this is cool. Right, I did the same instruction, and I stored my numbers in different locations in memory. They're all still in there. If I had said move WREG into temp, right, I would have overwritten it each time. Here I've got them all sitting in memory, and they're in different locations, yes.
Is your goofy benefit that when you use bypop, you don't have to pre-increment?
No, that's goofier.
Is it W?
Goofier than
You
that?
just have to check the work with it.
It's goofier.
Does it somehow like loop around to the first address again?
If,
So that
if,
space is free?
if you push too much onto here, eventually this will wrap around.
So does automatically incrementing then provide that first space to be free for it to wrap around?
No, it's actually kind of a bummer having this, like, not have anything in it. I'd rather not. And usually, you do a post-inc. Okay, most systems, when they use a stack, they actually do a post-inc. They would write something here, and then they would increment. Some processors, like ARM processors, they will let you fully specify when you work with a stack, whether you increment before or after, where you leave the stack pointer pointing, all this kind of stuff. It gets into a little bit of religious wars, but there's a particular reason I did it like this.
Oh, are you going to throw the stack pointer there? Are you going to throw the stack pointer there?
No, this is our fake stack pointer. So this is a stack, okay? This is like the call stack. When I do a push, it pushes something onto the top of the stack and it moves the stack pointer. And I'm using FSR 0 as my stack pointer, right? And I've decided that my stack is going to start at location 80 when I initialized FSR with 80. And my stack is growing in this direction with increasing registers, okay? That's just all kind of random. I could have made the stack grow the other direction. I could have started anywhere I wanted. I could have used FSR2. This is just one particular way I set it up, but it is a stack, okay? And FSR is my stack pointer in this case. Now when I say my pop, right, that's saying move FF, and it's saying post deck 0, comma arg. My arg is always W ridge. Sorry, my arg is temp 1. I want it to be different. So I'm popping off into temp 1, which is just another memory location. So when I say my pop, it's a move FF. So post decrement 0, what does that mean?
Decrement last.
Say again?
Decrement last.
Post means decrement last. So this says, take what the file select register is pointing to, copy that into temp 1. So FSR is 83, contents of 83 is 30, that'll take a 30 and load it into temp 1. And then after doing that, it will decrement FSR. So then it changes this to 82. And in here, I cleared out W, and now I'm just adding this to W. So W is equal to 30. And then I do another my pop, which says, take what FSR is pointing to. Well, FSR is 82, so it's going to take the number 20 and load that into temp. And then I add W to temp and put it back in, so this is 50. And then it's going to do a post deck. And then I'm going to do the add. And then in my third my pop, it says take what FSR is pointing to. That's an 81, it's pointing to 10. Copy that into temp. Decrement FSR. And then my add instruction takes 10 and adds it to that. 60. So, a couple of things to note here. Because I did a pre-inc, I had to do a post-dec. Okay? If I had done a post-increment, I would have to do a pre-decrement. Right? Why didn't I want to do that?
If you did a post inc, you would have your values move one location up, right?
Right.
Yeah, you never get that first number that you when you want to pop, right?
Well, you could. The reason I didn't do it is because there is no pre-decrement instruction.
Where's my second?
Right here. I
Yeah.
have no pre-deck.
I didn't design it.
But there's a posting.
Yeah, there's a post-inc, there's a post-dec, and there's a pre-inc.
Interesting.
Yeah. They could have gone crazy and made like 1 million registers for this, but I guess they said, nope, you got 3, you're cut off. Get out of here. So that's why I did it in that order. But that'll come up when we look at some C code. If you do 3 pushes and you do 3 pops, your stack pointer ends up where it was before. Okay. Also, the things I pushed on the stack, they're still on the stack. Right? They're still sitting in memory. Just because I moved them into temp, they didn't disappear from memory. Memory always has stuff in it. Okay? But my stack pointer is such that the next time I push something, it's going to overwrite this number. Okay? But that stuff is still sitting in there. There's been some exploits done on this, by the way. The fact that when you return from code, the contents of your stack still has information in it. If you have the same stack space for a user mode as for a supervisor mode, you can have some privileged code running using the stack, pushing temporary variables onto there. And when you come back into user mode, you can go off and sniff the stack and possibly find stuff that was being used in supervisor mode. Passwords, personal information, stuff like that. So there's exploits that have been done with this. Most processors today, they have separate stack spaces for separate modes for that reason. again, it's this idea that like everything interacts with everything else. When your system gets more complicated, you have an operating system, multiple processes, you have hardware and software, and you have all these different things interacting at different levels, sometimes in unexpected ways. So, since we went through all that, I'll go ahead and execute this. So,
So how do you get the file registers thing?
on here I did view file registers. So this is our physical memory. File select register is presumably 80. W register we can read at the bottom here. So step 1 is W is equal to 10. Get 0A hex. And now when I say push it, here's location 81. That's where our number 10 got pushed. And file select register got incremented. We can't see that on here. And I put a 20 into W and I call my push again. There's where the 20 is, 14 hex. And I do another push of 30 and there's where 30 is. So there's our contents pushed onto our stack. And if we did another push, it would go on the next location, 84 hex. And then I can start popping off. And I'm popping off into temp 1, which I set up to be at location 0. So on my first pop, the bottom of my stack, which contained 30 decimal, gets loaded into temp. And the next pop it loads 20, and the next pop it loads 10. And W gets incremented down here and ends up at 3C hex, which is 16. That all works. So stacks, what are they good for?
Absolutely.
Say it again.
Confirm the queue.
Stacks are useful.
We've got stack frames, perfect code, and stack overflow errors.
Yeah, they're a good way to generate errors.
I have a question.
Okay.
What's the difference between a stack and a heap?
Oh, heaps are much more complex.
Yeah, we're not doing
So you don't want to know like how
no
things
heat
work.
tops, both sides.
The thing with a stack is usually you push things on a stack and you take them off in the opposite order. So it's a last in, first out, or a LIFO. Okay? Heaps don't have that restriction. You can say, I want 1,000,000 bytes of storage from the heap and get 1,000,000 bytes, and somebody else can say, I want 1,000,000 bytes, and each of you can release it in a different order from when it was granted. Okay, that's something that's hard to do with a stack, because you really just sort of put into the top and take off from the top. So heaps are usually used, like when you use a malloc function in C, to get a bunch of memory, it's really coming out of a heap. And it's just a big structure that the operating system keeps.
Is there a size limit to keep when your program is executed, or
Size limit to the,
what's it keep?
there's some sort of limit, but usually like in Java you can do a switch to make it whatever size you want, up to the limits of your virtual memory basically.
Java it's static, I mean, in C programs, is it dynamically done for you, or
I think the heap is probably an operating system resource at some level, because you can just malloc as much as you want, and until you run out of virtual memory, we'll give it to you. All right, so why stacks? All right, so you comfortable with C? You love C? Sure. C is great.
Reading or writing? Comfortable with? We hung out for a while. You can read computer someone.
All right, there's some fairly harmless C code. It's a subroutine or a function declaration. And I declare 3 variables in here, I, J, K, and I do some really marvelous things with I, J, and K. And great things happen, and then I return.
you need to return the message?
I don't like using void, but I like making the compiler work. All right, here's another subroutine, sub2. Kind of looks the same, does different marvelous things with I, J, and K inside, right? So if I say I equals J equals K equals 1, call sub2, you don't say call and C. But, and in here I say, set these equal to 17. And I come back from my subroutine, what value do I, J, and K have down here?
I've heard this one before.
Three variables get on the code.
1, because it's not global.
Right? The scope of these is local. Right? They're defined inside the subroutine, so they're local to this subroutine. I, J, and K here are local to this subroutine, so when I change them over here, this instance of I, J, and K only exists in here. When I come back here, I'm back to these I, J's, and K's, which I set equal to 1. Okay, now if I return them from the function or I pass addresses, I can change them. But in general, these are local variables. Okay? These are local variables. So, how do we implement this in assembly language? If you were going to write your code for this in assembly, how do you declare variables now in assembly language? Yeah, so you say something like I equals 20, J equals 21, K equals 22, or something like that, or you put them in a C block. But at some point, the assembler would say, okay, the address for variable I is 20, the address for variable J is 21, K is 22, right? Hopefully, if I had sub2 declared in my same file and it saw this, it would say, okay, this is going to be 30 and 31 and 32. We'll put them at somewhere different inside memory. Okay? Suppose sub1 calls sub1. Yeah, you'll like this. Right? What if my subroutine is calling itself?
What if against that?
I'll have some code in there that'll not call itself forever.
Doesn't it still reinitialize the variables?
In C, it'll reinitialize it. In assembly, you can't be using your static variable declaration to do that. So you'll have to
Right,
use-
like, but in a C, like, if you ran through that code, it's still gonna say this variable equals at the beginning of it, so it's gonna start it all over again.
Right, so I'll call sub1 and then I'll say I equals J equals K equals 17. And I'll call sub1 again. So when I get down here, what's my value of I, J, and K?
So, 1.
Yeah, it's either 1 or 17.
When you call a sub, it
Maybe
takes
someone would
more
say
room.
2 just for variety. Right? I initialized these local variables to 1, I did something, then I initialized them to 17, and I called sub1, and sub1 set them to 1, and for some reason it decided to return right then. When I get back here, IJK will still be 17. They're local. They exist only within the scope of this instance of this subroutine. Okay? Did you do any recursive code in your programming classes?
Hell yeah.
A little bit.
Okay.
Outside of it, it's more than inside, but yeah.
Like you can write factorials recursively if you want, by calling yourself. Recursive code only works because when you call this instance of sub1, it has its own copy of IJK. Okay, they're really local to this particular call of the subroutine. And if I call this subroutine again, there's another instance of these variables IJK. Now, if I take this and I run it through my discount rate compiler, and it says I equals 20, J equals 21, K equals location 22, right? My recursion's not going to work. Because down here in this instance of the subroutine, it's going to take location 20, 21, and 22. It's going to store 17 in those. And when I come back, I've changed the values of these variables. They're not actually local. They're still kind of global. So to really get a local copy of your variables, you can use a stack. And the way you would use a stack is when you go into your subroutine, you would do the following. I would say something like add 3 3 to my stack pointer. So here's my stack. Here's the initial stack pointer. I'm going to say add 3 to that. So it's going to go 1, 2, 3. I'm going to put my stack pointer here. And I'm just going to say, this is where I'm going to store I, this is where I'm going to store j, this is where I'm going to store k. And remember, my stack pointer was sitting here, so these locations were unused. I've moved my stack pointer down here, so if I do any calls or push anything on the stack, it's going to start this location on. I've basically reserved 3 locations in memory, dynamically, that I'm using for I, j, and k. Okay? I can do some other stuff, and if I call sub1 again, in the beginning of sub1, what it's going to do is it's going to add 3 to the stack pointer, and I'm going to pretend that this is I, and this is j, and this is k. But these are separate copies of my variables. In that second instance of sub1, these are the variables it's going to manipulate. Okay? And when it's done, it will bump the stack pointer back up to here, and now I'll be working with my first instance of my variables. So this is a typical way that a compiler sets up local variables as opposed to global. If you want a global variable, you just say I stored at location 20. Anybody that uses I uses location 20. If you want a local variable, I would say let's say file select register 0 is my stack pointer. Okay, I would use file select register 1, and I would copy register 0 into register 1 to preserve it, and then I would add 3 to the stack pointer. And now when I want to access I access whatever is pointed to by file select register 1. J is file select register 2, K is file select register 3. Or, 1 plus 1, register 1 plus 2. It's making some sense?
Does it identify the variables by the process they're associated with? Like you have 2 i's, but one of them's with sub1 the first time it got called, and then the second one's the second instance of sub1?
Basically, yeah.
Okay.
When you enter a subroutine, there's some setup that takes place to do this kind of stack pointer adjustment to remember where things are, but it has to be agreed upon by everybody. Okay, so at the beginning of the routine, you say, this is the universal stack pointer. I'm going to bump it up. I'm going to use these locations to store my local temporary variables. When you exit the routine, I would take the same stack pointer, I'd load that back into my stack pointer, which moves it up here, and now this space is available for something else to use. But while I'm in my subroutine, if I call some other piece of code, including myself, these locations are still preserved. And that first instance will be using this copy of file select register 1 to access these. When I go into another one, it would take this and it would use this in a copy of SP1. Notice that when you do this, though, you're obliterating what's in file select register 1. You need to save that somewhere. Where do we save it?
On the stack.
On the stack. Right? So that when we exit, we get back the old value of file select register 1. And this lets us use exactly the same structure every time that we go into a subroutine. Take what's in file select register 0, copy it into file select register 1 after we push this on the stack to preserve it. When we exit, pop off the value of file select register 1, use that to restore file select register 0 and return. And on non-pick processors, you would also be pushing your actual return address on the stack and then popping it off when you return. This is also how you pass arguments to subroutines. Right? If you only have a few arguments, you can pass them in the W register or register 0 or something like that. If you have more arguments, typically what you do is the calling program pushes the arguments on the stack, makes an adjustment, and then calls the subroutine. When you get in the subroutine, when it compiled the code, it knows I've got 3 arguments coming in. It knows the previous 3 locations above the top of the stack. Those are my 3 arguments. And so it would take your incoming stack pointer, subtract 3, put that in some sort of file select register, and then use this as an index, with an index to pull off the arguments that were passed in. If you call a subroutine and you pass functions by reference, you pass the address of them, right? Same thing. You put the addresses on here, and now you can use what's stored here as a pointer into memory to actually get to the variable that was originally passed into you by reference. That's a lot of hand waving. this is set up for Tuesday, I guess we'll start looking at some of this in some actual assembled, compiled C code, and you can see what it looks like. I've got a few minutes, I'll start you on that in a second. Questions about this basic setup? The first time I encountered this, it took me about 3 weeks to like get any kind of handle on what was actually going on. So
Yeah,
it's
I
a
have a
little
question
muddy.
because I just don't know what to ask. It's just-
Yeah. No, just let it sink in, and I'll start looking at some C code here, and then we'll go into it more on Tuesday.
So what about pointers in our C code?
Pointers they're typically just addresses, right, of other things. So when you dereference a pointer, you basically load it into something like a file select register, and then use the indirect register to grab it. And I mean, at some level, they're really not any different. You can take an integer and use it as a pointer if you have a good compiler that doesn't argue with you, which is how you make like a little peek and poke function.
I want to know what this function is doing.
Yeah. Go through these examples on page 197, bottom of 196 and 197. I was going to go through these, but we've already gone through some of this in some detail. But these are a pair of good exercises to make sure that you understand what this indirect referencing is doing. So page 197, basically. Look at this, see if it makes sense, what's being modified here, and then this example here also. I'll go through more of this in detail on Tuesday. Well, let me just start you on one here. I just want to look at this section of code here. And Tuesday we'll go through the intro and the end stuff. Let's just look at this piece of code right here. Move FF FDE, comma 02, and move FF FDD, comma 03. What do you think this does?
Moving the content of that register to another one?
Yeah.
File select register 2.
Reversing order.
Could be.
Well, first we looked at
I
it.
mean, isn't that what it means? And move that contents of that file, to the contents of the second file?
Yeah, I thought it was to move like
That's the
the
contents of
contents
the
of
second file
FTE
address?
to the contents of 0x2.
Okay, so this moves from FDE, which is post increment 2, into location 2. So
Oh, you mean.
I'll go through the beginning later on, but for argument's sake, let's just assume that FSR2 starts off at A. Okay, it's pointing somewhere in stack space, and this is what you're using for a stack pointer. We'll look at the details of that later, but
You can tell us.
It'll copy 80 and 81 to position 2 and 3.
all right, go ahead.
They'll go positions 80 and 81 to 2 and 3.
right? So it takes what's pointed at, as it's going from FDE, it's a post increment, so it's going to take what's pointed at FSR, which is here,
Just call it OF80 for the value.
right? It's going to take whatever is stored here, and it's going to copy that into location 2. And then it's going to increment FSR2
Nope.
to 81. What?
Nope.
Nope.
Forget the
And
nope.
these nopes are just part of move FF. And then it's going to read from FDD into location 3. So FDD says read from FSR, which is 81. Let's just say this is C2. Copy that into location 3, and then do a post decrement. So this is going to go back to 80. What this has done is it's read 2 bytes from these locations in memory. It's copied them to these 2 consecutive locations in memory, and it's done it without perturbing FSR2. It's back to where it was.
Next, next will increment position 2.
Right, so it puts a 1 into W, and it adds that to what's at location 2. So it replaces C1 with C1 plus 1. And then it puts a 0 into W, and it says add W to the contents of location 3, but do it with a carry.
What's the F in the access? That's just add.
That says go back into the file, and that's using the access bank.
Okay.
So we can kind of ignore them. So it adds 0 to the contents of location 3, but it says also add the carry bit. The carry bit was set or not set when you did this adding 1 to C1. So it replaces this with C2 plus whatever the carry was from your first addition.
So it's going to be C1 plus 1 mod 255.
C1 plus 1, yes. And if it's a 0, this will be 2. So what this is doing 16-bit addition. Okay, here's C2. Here's C1. We add 1 to this number. If we got a carry out, we also add a 1 to this number. Okay, that's how you do 16-bit addition when all you have is an 8-bit adder. If you want to do 32-bit addition, you could keep doing this. If you got a carry out of here, you'd add 1 to the next byte. If you got a carry out of there, you'd add 1 to the 4th byte. So this is executing this count plus 1 part, assuming that our count was originally stored in these 2 locations on our stack. Okay, which it is, because in fact count's a local variable in this subroutine, and so the beginning part there basically moves the stack down 2 locations and leaves these available for your temporary variable. So we've incremented our count in these temporary locations 2 and 3, and then we just reverse the process. We take this at location 2, we store it at FDE, which is a post increment. So we take location 2 and we write it into what's pointed to by FSR. So this will be C1 plus 1. We increment this to 81. And then we move the contents of location 3 to post decrement. So it says take location 3, which is C2 plus possibly a carry. Write an address pointed to by 81, and then decrement. So that little section of code does this instruction, count equals count plus 1. And when it's finished, our temporary locations that are storing count correspond to count plus 1, and our file select register 2 is unperturbed, back to where it was at the beginning.
Can we turn it into a macro?
We could make a new language called C or D or something that would do this.
We'll call it D sharp.
So 12 instructions
That
to
doesn't
say
make
count
any
equals
sense,
count
does
plus 1.
Thanks.
Now if you had said count plus plus, the compiler might have avoided this and used an increment instruction. Okay, because again, the plus plus is an easy flag to tell the compiler I'm actually adding 1. Otherwise, you need, when you're compiling this, you need to actually look at the constant and say, oh, that's just 1 I'm adding, I can do an increment, which compilers do today. But originally, that was the reason for the plus plus or the minus minus, so you could just use an increment or decrement instead of going through the generality of this. So we'll dig into all of these examples on Tuesday and see how this storage gets set up at the beginning, and what happens at the end. And then, if you wanna look through these beforehand, that's never a bad idea. But, there's some subroutine calls here, so we'll see how you pass an argument to a subroutine and, return a value. And I'm probably not gonna go through a lot on types and structures and arrays, but I will look at some control structures. So we'll look at an if then else block, see how that gets coded up, and a while loop, and a for loop. And that will do us. And then I'll talk about everything else in the book. Alright, so that's enough of that. So go back to your labs, and we'll continue this.
One piece of data. Nothing to go.
Okay.
One piece of data.
Okay. Okay.
The charge.
Okay. Is there definitely a minimum that you need?
No, I was thinking this would be on the phone, right?
Mm-hmm.
So like having the extra statement stuff taken out of the phone.
Yeah. But I mean, if you're getting any current at all, is
You
that
get
enough to do a
current.
little charging?
Yeah, you can. There is even a little charging, but not
Yeah.
5 rolls per million.
Mm-hmm.
Now, if we are very, very lucky, our car will end in about the same place it was ending.
You could look at,
You'll be lucky, I have a good feeling about it.
Huh?
You'll be like,
the
it's
fact
got
that a cell
23
phone
minutes.
normally pulls like an amp out of its charger or whatever, it doesn't necessarily mean that you need it.
Oh. And I put
Yeah, you can probably get away with it 5 million.
I mean, you might be able to get away with a few million.
You want me to go try it out?
12 days. But you could try to look at some of that and come up with some
How bad is it?
It broke.
numbers or some graphs for, you know, different amounts of
Cool.